Come on, show me your recording. Okay, looks like we're recording. Okay, what we're doing here is video 34, and this is actually one of the cooler videos, I think, because it's going to be an example of multiple regression. And so video 34 and video 35 will actually be an example of multiple regression. What I want to do in this video is show how multiple regression using methods, matrix methods, with all quantitative predictors. Video 35 will actually get into what if we have a categorical predictor such as gender, school district, whatever it may be, as one of our predictors. And things can change quite a bit when we run into that. So guys, anyway, here's what we're going to do. First thing I'm going to do here is we're going to use matrix methods. So use matrices, and we're going to open a data set. From the desktop, convert to matrices. We're going to calculate the coefficient estimates. We're going to calculate their standard errors. We're going to look at the fitted matrix. We're going to look at residuals. We're going to look at the hat matrix. We're going to look at identity matrix. We're going to look at we're just going to look at all sorts of cool stuff. After matrix methods, we're going to get into creating an ANOVA table. Along with creating an ANOVA table, I'm going to show you some nuances, sort of, the way ANOVA tables are often created, and it's kind of the default that we see in R. We're also going to get into R squared, adjusted R squared. We're going to get into the inference, so we're going to be looking at the test statistics, the p-values, the confidence intervals, and the final thing we'll do here is see how matrix methods can be used to make estimates on mean responses and predictions of new observations. So this is a jam-packed video. I say we're going to be going right around an hour. But it's one of the, it's kind of actually a cool video, because you think about it, what we're doing is we're kind of putting everything together and that we've talked about in the previous videos and making it happen. So it's kind of like you've gone to the store, you bought that new golf club, you're excited to get to the golf course and hit it. Well, we're getting ready to hit the golf club. We're getting ready to do some cool stuff. So, guys, one of the first things I want to do is show you what I have right here. And I have a data set, it's called IQ Read, and I'm going to open that up in Excel format. And what I'll do is I'll upload this video. It will be uploaded on Blackboard on the main page, and I'll call it, very creatively IQ Read. And so if we can maximize this, I want to give you an indication of what, let me make that bigger so you guys can see it. All right, what we've got here is some kind of, a semi-cool data set. And I can see, we're all math professors and math teachers and math instructors, and this kind of data set could clearly show up in something we would be asked to analyze for our students or possibly our school district. So right here, they've got a reading score, and I think this reading score was taken from the Metropolitan Achievement Test, and it's the reading score on that. LSS is kind of a cool measurement. What they did is they let kids of this age group pick out 8 books. And an independent observer, probably a teacher or maybe even a team of teachers, looked at the grade level of the book. So this is the average grade level of the 8 books that the student chose to read on their own. To my knowledge, they didn't know that they were that this was going to happen. So, for example, this student right here, the average grade level for the books that they chose, the 8 books they chose, was 4, while this student right here, number 5, no, actually the 4th, chose books of higher reading level. Guys, here we have IQ. If you buy into that stuff, this column's for you. Personally, I've taken, I think, 11 IQ tests. I've never scored the same thing once, so who knows about IQs? EST is, this is a self-assessment. This is where the student estimated their own reading level. Guys, obviously gender is one of our first categorical variables. And over here, they actually got a school district. So apparently, these kids were randomly selected, or at least I hope they were random, from 4 different school districts. So the first video, this video 34 that I'm putting up right now, I'm only going to be concerned with these 3 variables. And the intent is going to be to predict read from LSS, IQ, and EST. So read is going to be the Y, and we're going to come in and choose our X's. This will be X1, X2, and X3. So we have a 3 predictor model. Now what I'm going to do is I'm going to shut this down, and I don't want to save. I've got it exactly the way I want it. And I've already got R up. So the first thing I've got to do here is I've got to get the data set open. It always helps me to get my working directory so I know exactly the form that I have. And then I want to set my working directory as the desktop. Now, I just being whatever, anal, whatever you want to call me, I always like to go back and check that the working directory is what I set it at. Now the next thing I want to do is I want to set this as my data, so I'm going to go read CSV. CSV stands for comma separated values, and I found on my computer, and I tried this out on my desktop as well, that I have more luck opening a CSV file on R than I do an XLS file. So gang, what I got here is I've got IQ read.csv. I encourage you to save it on your desktop as a CSV and open it the same way. Now, what I want to do now is I want to do data. No, I don't. Let's go data 1. And I want to do a data frame for data. So the data that I want to use here is going to be data 1. And when we do data frame on our data, this gives us a little bit extra advantage when we're trying to convert things into matrix form, or at least I think it does. Now, the very first thing I want to do, well, first thing I have to do is I have to attach data 1 so I can actually work with it. It's always easy to forget. And the easiest way to kind of check yourself on this is just try to take the mean of one of the variables. And if I had tried to do this before I attached data 1, I wouldn't be able to do that. Or at least I don't think I could. Once I attach it, that means I'm ready to do some to do some cool stuff. All right, so first thing I want to do is I want to create my X matrix. And recall, this is our design matrix. So guys, what I want to do here, first thing I want to do is set up a table of values. So if you remember, my first column in my design matrix has to be all ones. And if you look back at our data set, we have a 30 observations. So what I want to do here, first of all, is I want to go repeat integer, and I want to repeat ones 30 times. So now if I see my A's, I have 30 ones. All right, so that's really going to come in handy when I start setting up my matrix X. Guys, next thing I'm going to do is I'm just going to go for it. So I'm going to set up my matrix, and I want to bind together certain variables. So I'm going to do that with the C operation. So the first thing I want is A. The next thing I want is LSS. The next thing I want is IQ. And the next thing I want is EST. So I'm going to have a 3 predictor model. Hopefully you know by now that the next thing you're going to do is you're going to set up your rows. So I want my n rows to be 30. I want my number of columns to be equal to the ones, LSS, IQ, EST. So the number of columns is going to be always one more than our number of variables. And I've got to tell the program that I want by row to be false. I didn't enter my data by row. I actually entered it by column, because I've entered column, first column, second column, and so on. So guys, when I do that, I always like to just check it, and you can see I've got my matrix X, which works out really cool. Okay? Now, next thing I need to do is set up my Y matrix, and that's really easy to do, because my Y matrix will be just read. So in row will be equal to 30, and in column is equal to 1. And again, by row equals false. Guys, I've been told, I've never, believe it or not, I've never even tried it. I always put false and true in capital letters. I'm not sure if it works the other way or not. I'll tell you what, let's try it. Wow, that's crazy. Okay, well, we learned a valuable lesson, didn't we? C read. In row equal 30. In column equal 1. Alright, so guys, now we got our Y matrix, and life is good. So what I want to do first of all is I want to create my beta estimates. So I'm going to call that B. So guys, the first thing I have to do is I have to take the product of the X transpose X, but I have to take the inverse of that. So to take the inverse, I take solve. I want the transpose of X. Remember, we can't just do multiply. We multiply matrices. We have to do percentage sign times percentage sign and times X. So this part right here takes the X transpose times X and takes the inverse of it. Well, the next thing I need to do is to take the transpose of X again. And the next thing I need to do is take my Y matrix. So guys, now we can see that we have beta equal. Notice we have four values. So therefore our model is going to be, read can be predicted by taking the intercept, negative 26.55 plus 2.32 times, I forget, what did we put, LSS first? Yeah. Plus 0.47 times IQ plus 6.61 times EST. Now, interpretation. So the interpretation of LSS, the beta coefficient estimate is 2.32. So what we would say here is we would say controlling for IQ and EST, the predicted read increases 2.32 units with each unit increase in LSS. All right, gang, so what that tells you is imagine well, arithmetically in terms of the prediction, what we could do is we could hold IQ constant. Kid has IQ 105. So we want to let all kids of IQ 105 who estimated the reading level to be whatever it may be 6. Well, we can let LSS vary, and we could see that the predicted read would vary 2.32 units. Let's go another interpretation for IQ. Well, we would say controlling for LSS and EST. The predicted read increases 0.47 units with each unit increase in IQ. Guys, similarly for EST, I'm not going to write it, but it would be controlling for LSS and IQ. The predicted read increases 6.61 units with each unit increase in LSS. Now, guys, this is really super important. Why is multiple regression so important to us? Because what it allows us to do is to partition out the variation in read that's attributed to these different things. Now, we know, or we should know, that, let's say you buy into this whole IQ thing, and I do a little bit, but not as much as most people. But this LSS right here, the average level book that these students went over and selected out of the 8 books that they selected, in some way, shape, form, or fashion may or may not be attributed to their intellect, their aptitude. Well, what we've done here, and it would make sense, I don't know much about reading. I haven't studied reading scores and reading education data like I have math education. But the LSS, I would think that, more intelligent kids, higher aptitude kids would be tempted to go over to let's say you had free reigns at the bookmobile. I would think that higher IQ kids would be more likely day in, day out to choose higher level books. I don't know that, but that's actually what our model is actually testing here. So we could say that LSS, part of the variation in LSS is probably attributed to the kid's aptitude level, the kid's intelligence. Well, by us entering IQ into the model, we control for the variation in LSS that is attributed to the kid's IQ. So it's completely controlled for not only arithmetically, but it's controlled for statistically. The EST stands for the predicted, the kid estimating their own reading level. Well, it may be argued that smarter kids are going to predict they have higher reading levels. I don't know that to be true, but that's what we do in statistics. We make hypotheses, we make educated claims, so we go out and test, gather our data, and we make those tests. So by doing that, if either one of these measures, LSS and EST, appear to be highly related to, and don't get too comfortable with that, because it actually turns out if we get 2 variables that are highly related, we get into something called multicollinearity, which is bad. So, but if we can think of the variation in LSS or EST or any of the combination of these, we want to put that variable in our model to control for it. Okay, the next thing we would want to do is we want to come in and get our standard errors for our betas. So next, we'll calculate the variance covariance matrix for our betas. Now, guys, you can't lose lose focus here and realize we have variance covariance matrices for betas. We have covariance matrices for our errors and residuals. This is the one that we're going to use for our betas that are going to be helpful, actually necessary, when we actually get into the inference part where we create our test statistics. So guys, remember, this can be calculated by taking our mean square error times x transpose times our x, and raising that to the -1 power, taking the inverse of that. So can't do that in R. I have to actually work this out. Guys, first of all, we'll calculate the mean square error, and the sum of squares for the error, which we'll need later, is calculated this way. The sum of squares for the error is calculated by taking, so I'm going to take sum of squares error term here, and this is calculated using matrices as transpose of y times our y minus our transpose for our beta times our transpose for our x times our y. So our sum of squares error is going to be 8909.853. Now guys, remember our mean square error is found by taking the sum of squares error divided by our degrees of freedom. Now in this situation, our degrees of freedom are going to, for the error term, are going to be, well, this gets kind of complicated. Okay, I'll tell you what, let me get out of here and go back to this. Now this is complicated even for me. It depends on it depends on how we do this. Okay, if we're looking at our sum of squares for the error, for example, and in matrices form, this is exactly what we did. Now, depending on how we set up our model, if we set this up, guys, I'm just trying to be thorough here, as having p minus 1 predictors. If we set it up this way, then our degrees of freedom for the error is going to be equal to n minus p. So in our situation here, we're going to have 30 minus, we have 3 predictors, so 3 predictors minus, so p minus 1 is equal to 3, so clearly p is going to be equal to 4. So we're going to have a degrees of freedom of 26. Now, a lot of books don't do that. And if all the books did that, I would stop right now. A lot of books, and this is really the way that I prefer it, set up our model as having k predictors. Well, in this situation, instead of n minus p, we're going to have n minus k minus 1. So, you know, that should make a lot of sense here. In our situation, we would have 30, and we would have minus 3 minus 1, and is going to give us 30 minus 4, which again is going to give us 26. You know what? I really don't care how you remember it. To be honest with you, I'm gonna go back and forth. But the one thing that we all can agree on is that we have degrees of freedom 26. Now, guys, I'm not going to make any major changes on you without telling you which one I'm using. And in most situations, I'll probably use both. So, guys, what I can do here is I'm going to come in and divide this by 26 to get my mean square error. So we can see that my mean square error here is 342.6867. Now, why do I need that? Well, guys, I need that for the standard error for my betas. So my standard error for my betas is going to be the mean square error times, now I want to put this in, so I need solve transpose x, shoot, yeah, is that right? Yes. Okay, that's fun. Well, I am completely confused why this isn't... Well, gang, I have no idea. I think what we're going to have to do is set it up this way. First thing I'll have to do is I'll have to look at this, and then I'll have to take my standard error for the betas, and I'll have to take the value 342 point, yeah, I think this is going to work, 67, and multiply it by my standard error. So standard error for the beta, yeah, that works. That's really strange that wouldn't multiply that out. Okay, all right, anyway. So remember that, make a note of it. Now, what's important here, if you look at the non-diagonal entries, this is the covariance between, for example, our second predictor, which would be LSS, and our first predictor. So this has a covariance of negative 41.94. Notice the covariance, you know, it's a lot like correlation, except correlation has to be from -1 and +1 because it's standardized. It takes the product of z-scores. Notice that the covariance does not. But what's important to us here is the variance on the diagonals. Now, guys, remember, this gives the square of the standard errors. So to get the standard error for our intercept, we got to take the square root of 1067.794951. To take the standard error for LSS, we have to take the square root of 8.9865 9661 to find the standard error for IQ. We got to take the square root of well, we got 0.08932 687, and to get the standard error for EST, we have to take the square root of the last diagonal, which is 9.842429. Yes. Now, kind of thinking ahead, where are we going to need the standard errors for our betas? Well, we're going to need those when we get into our inference, where we calculate the test statistic, and we get into into those things. Okay. Now, the next thing I want to do is I want to calculate our fitted values. In other words, our predicted values. So guys, remember our fitted values deal with the hat matrix. So the very first thing I'm going to want to do is create the hat matrix. And I'll tell you what, let me look something up here real quick. Okay, our hat matrix, which I'm going to be real creative and call it hat, is our x times the inverse of transpose x times x times our transpose x. You guys, our hat matrix is going to be a big old 30 by 30 matrix. Fun, fun, fun. Hopefully I don't require you to write anything like that out. And guys, remember our fitted matrix is our hat matrix times our y matrix. Okay? So I'm going to call it fitted. So this is going to be hat times y. So our fitted matrix gives us some cool stuff. Using our model, if we put in the x values, for example, for the first observation, this is going to well, I'll put it this way. Here in a second, I'm going to put this all in one data frame, one table, where we're going to see what we get there. Okay. Now, our residuals. And these are actually harder to do with. I'll tell you what. Let me write this out so you guys can be more thorough in your notes. The residual matrix. As I told you in video number 33, I think it was, requires the identity matrix. And it turns out that our residual matrix you know what, really? I guess the easiest way to get our residual matrix would just be to do residual and to do our observed y's minus our predicted y's. So our residual matrix would look like this. Now guys, what I want to do now is I want to do let's do data frame, and I want to look at kind of get an overall picture of our data. So I want to come in with LSS was the first predictor, IQ is the second predictor, EST, then we had read. Then I want to come in with the fitted values, and then I want to come in with the residuals. And that's not going to work. Let's see, what would be the best way to do that? Is a data table? No. not data frame. Guys, we've done this I don't know how many times, and I have just drawn a complete and utter blank. And I have no notes prepared on this. Shoot. Let me look back through some old, I've got some stuff I scratched down here. I'm drawing a complete and utter blank on the way to put this. It's not really actually something I need to do or have to do, but I want you to see the darn it. Huh. Well, that's just lovely. Okay, read. That's not it. All right, guys, I'm too deep into this one to turn back. Let me go back to some notes and see if I can find something. I thought for sure it was data frame, but it's turned out it's not. I hate when this happens. And it just happened. Okay. I know you guys are sitting there telling me exactly what I need to do. Sorry, boys and girls. I hate it when this happens. Well, I'm not finding anything. Well, I'll tell you what I'll do. I'll just get out of here and go into Google. This is not it. Okay, data frame. That should. Guess I've used this and I don't know how many previous. Oh, daggone it. You guys are probably sitting there screaming at me right now. You didn't call it RES, you called it RESID. Okay, wow. So those kinds of things that drive me completely batty, something little like that. All right, if you see what I did, I put this RES, and right there it says RESID. And if I just paid attention, my error told me that. All right, gang, so let's, what we're doing here is for the first observation, for example, from LSS, IQ, and EST with a read of 55. Using this student's LSS, IQ, and EST, we would have predicted this student to have a predicted read of 66.48. Well, notice the residual is negative 11.5 because the read is about 11 units less than what we predicted. Now, this gives you a really nice way to look at your data. I like to look at the residuals, any residuals that seem to be unusually high or unusually low. For example, this one kind of concerns me. This student had a reading level of 10, yet our model predicted this person's reading level to be 60. So if this was a data set that that I was truly interested in from an academic perspective, I would suspect that may be a typo. And I think that would be something that I would want to investigate. If it's not, this could clearly represent some sort of learning disability, because when you have a huge discrepancy between the person's aptitude and their achievement, then that typically indicates a learning disability. So I don't know what's going on with this guy right here, or girl. I have no idea gender, but we could certainly look. I don't know if there's any others that large or not. So anyway, gang, we've got the residuals. So next thing I want to do, just to illustrate, is I want to do the variance covariance matrix for the our errors / residuals. Now, this is found it's found by taking our mean square error times our identity matrix minus our hat matrix. So the first thing we got to do is we've got to create a hat matrix, and we've got to we got to create our identity matrix, and we got to use our hat matrix. So the easiest way to do the identity matrix is to do diagonal 30. And what this is going to do is it's going to create a 30 by 30 matrix, but it's going to create on the diagonals our ones, which is exactly what we need for an identity matrix. So next thing I'm going to do is I'm going to just store this as like n, or whatever you want, and I'm going to take the identity matrix minus the hat matrix. Well, it's a day of just messing up, isn't it? And we get our n matrix here. Now, I've got to multiply that by the mean square error, and the mean square error was way back here someplace. So the mean square error was 342. Well, I really didn't need to go back there. All I need to do is just do mean square error, right? So I need to take, so I'm going to do standard error for the residuals. And I'm going to take 342.6867. And I'm going to multiply what I call that the n matrix. And we get the the standard errors for the residuals. Okay. Now, what I want to move into now is I want to move into creating our ANOVA. And I want to get out of R, and I want to get back into the blackboard here. So gang, what I'm going to do here is I ultimately want to be able to create, so we're going to have our regression, we're going to have our error. Well, this is typically referred to as residual. And I want my total. So the first thing we'll have is our sum of squares. Next thing we'll have is our degrees of freedom. Next thing we'll end up with is our mean square term. Next thing we'll end up with is the F and the p-value. Okay? Now, we already know that the sum of squares for the error is 8909.853. So I'm going to make a note of that on the blackboard under sum of squares for the residual. Now, we already know that the degrees of freedom for this were n minus p or n minus k minus 1. And we know that that is 26. And when we take the sum of squares divided by 26, we get 342.7. Now, just so we're all on the same page here, you can see what I've done is this right here. Now, arguably, some people think it doesn't matter. Some people think the total. Some people think the regression sum of squares is easier to find. I mean, you know, we're not doing it by hand, so I don't think it's a major deal. So I'm just going to find the total sum of squares. And remember, if we can find one of these, all we have to do is subtract the residual sum of squares from the total to get the sum of squares for the regression. So let's go do that. So guys, what I'm going to do now is I'm going to do the sum of squares for the total. And the sum of squares for the total takes the transpose for y times y. I'll tell you what, I don't think it would be an issue if I did that, but because I am overprotective of stuff like that, I'm going to put that in parentheses. Then I'm going to go minus, so we have 1 over n, so I need to do 1 over 30 times, then I need parentheses transpose for y times our J matrix. Darn it, forgot to do the J matrix. Alright, forgot all about that. So gang, let's create, sorry about that. Let's create the J matrix. So guys, just remember the J matrix is a matrix of just all ones. So I would create the J matrix here. And I would probably go repeat, let's do this, C, repeat integer 1 30 times. In row would be equal to 30, in column would be equal to 30, by row equal false. So my J matrix is just this enormous n by n matrix of all ones. So guys, what I can do now is come in and do my sum of squares for the total. And now I'm going to do transpose y times y minus 1 divided by 30 times the product of transpose y J matrix y. So our sum of squares for the total is going to be 15,771.2. So guys, we can clearly do our sum of squares for regression by just taking our sum of squares total minus sum of squares for our residuals. So gang, our sum of squares for the regression is going to be 61.3. Now let's go back over to the board. Guys, our degrees of freedom for the regression term are either p minus 1 or k, depending on what you get. So we have 3 predictors. So this is going to be equal to 3. Degrees of freedom are additive. So this will be 29. So what you can gain from this is that the degrees of freedom for the total will always be, regardless of whether the number of predictors is p minus 1 or k, the degrees of freedom for the total is n minus 1. So guys, remember, sum of squares for regression, sum of squares for our error residual. These things are additive, so this number plus this number must equal this number. Remember, degrees of freedom are additive, so this number plus this number must equal that number. All right, gang, let's make it happen. Get our F statistics. So the mean square regression is just going to be 6861. I'm just going to grab the calculator here. 0.3 divided by 3. So we're going to get 2287. .1. And remember that the mean squared terms are not additive. So gang, I don't ever want to see you putting a value right there, because what we get by taking 15,771.2 divided by 29 will not be equal to 2287.1 plus this. Now, I encourage you to try that out if you want to do that, but all right, guys, what we need to do now is get our F statistic. And remember, our F statistic is just our mean square regression divided by our mean square error. So I'm going to take 2287.1 divided by 342.7. So give me a break on rounding error, or rounding, not rounding error, but we get an F statistic of 6.67. Okay? Now, what are we doing here? Here's what we're actually doing. What we're testing with the ANOVA table is we're testing H sub O that beta 0 equal beta 1 equal beta 2 equal beta 3 are all equal to 0. So none of the coefficients are statistically significant. If we reject the null, and I have no idea whether we're going to reject it yet or not, it's going to be based on our degrees of freedom with a test statistic of 6.61. So our alternative hypothesis is at least one of the b sub k's is not equal to 0. All right, gang, what we got going on here is we've got the F distribution, which looks like a positively skewed distribution. We've got our F statistic here, which is equal to what, 6.67? So our area to the right is going to give us our p-value. Now guys, we're going to use PF, but remember PF gives us area below. So area under the probability distribution will give us an area of 1. So gang, it'll be easy to do here. So we're just going to take that our p-value for F is going to be equal to 1 minus PF 6.67. Our degrees of freedom for the numerator were 3. Degrees of freedom for the regression was 3. Our degrees of freedom for the residual or the error term was 26. So guys, our p-value for the F is 0.0017. I'm going to write that down real quick. So at the 0.05 level, for alpha, we would reject the null. So what does that tell us? Well, that tells us that at least one of our betas, so we are rejecting this based on our data, this statement is more believable. So either LSS, IQ, and or EST appear to be statistically significant. Well, that's good. It leads us into the next part. I'll tell you what. Let's back up here. Before we get there, let's get into the descriptives. And the first thing I want to calculate is the coefficient of determination, which is r squared. Now this thing's really easy to calculate because it's just the sum of squares for the regression divided by the sum of squares for the total. And I forget what those are, but we can clearly go back and find those. So sum of squares for the regression divided by the sum of squares for the total is going to be 0.435. So this is going to be 43.5%. Now, what this tells us, the interpretation would tell us that we can say that 43.5% of the variance in read is explained by the regression on the set of predictors LSS, IQ, and EST. You might be the glass is half empty here and say that 56.5% of the variance in read is explained by something else, by other predictors. 43.5%, and I don't like these lines in sand. Statistically speaking, when you take good quantitative, you guys got into this with the likelihood stuff. When you take good quantitative data and you create lines in the sand and dichotomize it, we restrict the variation. And to me, that's a statistical dilemma. Not a statistical dilemma. It's a statistical nuance and a statistical screw up to take a good quantitative measurement and dichotomize it. So I'm not going to do that here. Is it too high, too low? I'm not going to do that. It's just 43.5% of the variance in read is explained by the regression on our set of predictors. Now, we can show that as the set of predictors increases, our r squared tends to be artificially inflated. So Uh, since we have three predictors, our R squared is probably, very likely, in fact, overestimating, uh, overestimating, if I get that right, yeah, the variance in read that's explained by the set of predictors. So what we do there, and I'm going to scoot back over here to the air server. What we want to do there is we want to come in with what's called the adjusted R squared. Again, when you're doing simple linear regression, when you've got one predictor, this is perfectly fine to calculate and throw all the eggs in one basket. If you have two predictors, there's not going to be a lot of difference between the adjusted R squared and the R squared in most cases. But when you get more predictors, this becomes the standard, the adjusted R squared. Guys, this is pretty easy to find. It's just 1 minus. I always remember it. All right, I always remember that the sum of squares for the total, the degrees of freedom go on the diagonal. And this is just the way I've always remembered it. The degrees of freedom for the sum of squares total goes up there. The degrees of freedom for the sum of squares for the error goes right there. So gang, if we can get this calculated, life is going to be just super, super good, right? So this shouldn't be any problem to do. Go back over. So we need the so the adjusted R squared is going to be 1 minus. So first of all, I need n minus 1, which is 29. And I need n minus p, which would be 26. And I need to multiply by sum of squares for the error, sum of squares for the total. Guys, the adjusted R squared is going to be 37.0%, or well, 36.99% if we go out two places. I think I'll do that. So the adjusted R squared is going to be significantly less. Not statistically significant. I've got to be careful with that. It's going to be quite a bit less, right around almost 6.5 units, yeah. So the adjusted R squared would be something that would be much better for us to depend on. So we would say that approximately 37% of the variance in read can be explained by the regression on the set of predictors, LSS, EST, and IQ. Now, guys, I want to show something on. I want to demonstrate something to you that's going to be a nuance. If we do the ANOVA table using R, so guys, the best thing we can probably do here is first of all create our model. So our model is going to be, our linear model is going to be read tilde LSS plus IQ plus EST, right? So if we just do model, it's going to give us the coefficients, and you can see that the coefficients, line up with what we showed earlier for our beta. Now you can do a summary here for model, and it's going to give you some standard errors and our different things. And I encourage you to go back and look at the standard errors. I actually did those right, so I think I did standard error intercept. C32.6771. Again, what I'm focusing on right now are the standard errors. Forget just the center part. This part, the column under standard errors. The next thing I did was the standard error for, LSS was 2.9978. We did the standard error for IQ, which was 0.2988. And you can see that everything is, of course, matching up, which is always cool. we've had some videos before where it did match up, right? So now, if you want to get fancy here and look at an ANOVA table, now what I want you to concentrate on is right here. When we did our F statistic, our F statistic analysis, we rejected the null, which said at least one beta is statistically significant, not equal to 0. Statistically speaking, we cannot determine that LSS is different from 0. Statistically speaking, we cannot determine that IQ is different from 0. But statistically speaking, we have reason to believe that the beta estimate for EST is statistically significant and different than 0. So, we're going to demonstrate that in a second. Something else I want to show to you, it's a common mistake for a lot of people. They think the bigger this estimate is, the better chance it's got of being statistically significant. And it turned out in this situation where our largest estimate was the one that was statistically significant. However, if you look at the estimate for 0.4749, you've got to take in consideration that the t-value and the p-value are based on the standard error. So you could have a small estimate divided out by, relatively speaking to the estimate, a larger standard error, and you can create a t-value that's, so anyway, you don't necessarily, the estimates that's the biggest here doesn't necessarily lead to statistical significance. And that's important enough to actually say something about it. For example, what if I wanted to predict first-year college GPA by taking an ACT plus SAT score? Let's say we have a group of students who took both scores, ACT and SAT, and we wanted to use those two scores to predict first-year college GPA. Now, if you think about it, the interpretation of these coefficients at the end of the day is controlling for the other one. If we increase SAT, ACT, whichever one we're focusing on, by 1 unit, the beta coefficient is the change in the first-year college GPA. So let's just say, for instance, that I don't want to put numbers in there because I don't know how it would turn out. Nevertheless, what I want you to focus on are the interpretations for, first of all, ACT. So if we were going to interpret the coefficient for ACT, we would say controlling for the SAT score, the predicted first-year college GPA will whatever the ACT is will increase according to what the coefficient is and for the ACT. It's kind of hard to explain without numbers there. SAT would be the same thing. We would say controlling for SAT, controlling for ACT, the predicted first-year college GPA will either increase or decrease the amount of the beta coefficient for SAT. Guys, at the end of the day, what I want you to focus on here is a difference in 1 unit the same for ACT and SAT? And absolutely it isn't. ACTs tend to range from about 6 to 36. SATs tend to range from about 200 to 800. A person with a, for example, 30 versus a person who has an ACT of 29, again, 1 unit difference, that's a completely different comparison than someone, for example, who has a 600 and a 601 on the SAT, just because of the unit of measurement. So, let me go in and do the ANOVA. So this is going to absolutely drive you crazy. So if I do ANOVA linear model for the model, then we're going to get this. Now, I just want you to look at that. First of all, does that look anything like the ANOVA table that we created? Sorta. Sorta. Degrees of freedom don't look the same. However, we do have the 26. And if we add 1 plus 1 plus 1, we get 3, which, similar. Sum of squares for the residuals, for the errors, 8909. Well, that matches up. And then we get this partitioning out of the, instead of just having one line of regression, what it's done is it's partitioned out the sum of squares for LSS, IQ, and EST. All right, no big deal. Trust me, if you add those three numbers together, 2023.8, 33.16, and 1521.4, you're going to get 6861.3, just like we got for the sum of squares for regression. Now is when the fun starts. What they do here is they create what's called a sequential partition of the sum of squares. And when you come out here and look at the p-values, you're going to see statistical significance, statistical significance, statistical significance. Yet up here, you're going to see not statistically significance, not statistically significance, and statistical significance. All right, gang, here's what happens. This breaks down the sum of squares in partitions. This looks at kind of a hierarchical modeling in a sense. This sets out, first of all, and looks at the sum of squares for LSS. This probability p-value out here talks about the sum of squares being statistically significant. IQ has the nature, if you will, given that LSS is in our model, the additional sum of squares of 36 is it statistically significant. Now, in my opinion, this ANOVA table in this form, which we're not going to get into it this class because I'm already running behind, but our second class that I'm going to teach you guys either next summer or whenever we decide it's going to be, that's going to be the first thing we're going to talk about, is partitioning out the sum of squares. And it actually becomes very helpful in making important decisions. But guys, at the end of the day, what I want you to see from this is incredibly difficult to interpret in terms of estimating our coefficients, which we can do up here, which actually looks at the impact of one in consideration of the other three being in the model. It's not what's going on here. IQ is considered with LSS already being in our model. The sum of squares for EST is calculated with the consideration that LSS and IQ are already in the model. So it's a sequential calculation of our F value and our probability. Guys, at the end of the day, we don't rely on this to make decisions that we're interested in right now. Okay, now that that's completely and utterly confused, we want to start now looking at, hold on. Sorry. All right, well, the gang just got home, so it's going to get loud. So the next thing I want to do. Huh?
The gang.
Yeah, you're the gang. So the next thing I want to do is look at the inferences. And all I'm going to do here is I'm going to just look at the inference for IQ.
What?
Now, remember, guys, for inference, we need the test statistic. And the test statistic is going to be the beta for IQ.
The what?
I'm sorry, the B for IQ minus the beta for IQ over the standard error for the beta for IQ. And since we are going to be testing here,
it looks like it says fish. The IQ.
that our beta IQ is equal to 0 versus H sub A, the beta IQ not equal to 0, then we are going to have right here that equal to 0. So ultimately, guys, what we're going to have is we're going to have that our coefficient estimate, beta for IQ, over the standard error for beta IQ. Well, keep a running total here. We can go back to R. And what was our beta estimate for IQ? And we got that back there when we calculated B. And remember, the first was our intercept. The second was LSS. So 0.475 was the beta estimate. And we saw that we could find the standard error for IQ by 0.29. Well, let's just call it 0.299. So guys, what we're going to have, actually I want to stay here. So our T for IQ is going to be equal to the beta 0.475 divided by 0.299, and we get TIQ is 1.58. Notice that corresponds to our T of 1.589 right up here. And I'm going to go ahead and write that over on the chalkboard too, so we don't. Okay, now what we got to do is we got to calculate our p-value. You guys struggled with this a little bit on assignment number 1, so let's go back over here and talk about what this is. We're going to have degrees of freedom, a t-distribution, and we have 1.589. And we're going to look at the area above, but we have to multiply by 2 because we're doing a two-tailed test. Guys, this whole PT is going to give us area below. So what we have to do is take 1 minus and make the calculation. Now, for these calculations, the degrees of freedom are going to be let's see, our degrees of freedom for the estimates will be well, I forget. What are the degrees of freedom for the T? I'm pretty sure it's n minus 2 because we would have 2 degrees of freedom because we used, yeah. So guys, what we're going to do is we're going to use do our p-value for IQ. And this is going to be equal to 1 minus PT of 1.589. Degrees of freedom, we have sample size of 30, so we'll do 28. So p-value for IQ is 0.06. That's not going to be... Oh, I forgot to multiply by 2. So I need to take the p-value for IQ and multiply by 2. And you can see that we get not the right thing. Okay, let me think this one through, guys. We need... so we have found a t-distribution, which is a chi-squared. Let's see. So we're actually going to need, so our p-value for IQ is actually going to have to be calculated this way. So we're going to have 2 times 1 minus PT 1.589, comma 26. Yeah. So make a note, the degrees of freedom for the test statistic is n minus p when we have p minus 1 predictors, or it would be n minus k minus 1 when we consider k predictors. So guys, here if we have p minus 1 predictors, then p is going to be 4, so 30 minus 4 gives us 26. And again, if we have k predictors, which would be 3, we would have 30 minus 3 minus 1, which is also 26. So just however we look at that, that's going to be our p-value. And you can see that it matches with our p-value up here. Now you might be saying, well, sure doesn't match up with our p-value down here. It's not going to. Again, this is the ANOVA table. This is our analysis of variance for the regression. Here we're partitioning out the sum of squares and looking at the p-values for that. That's something completely different than what we did before. All right, gang. So we've got our test statistic. We've got our p-values. We've looked at at the inference. So the next thing I want to do is I want to look at the estimate the mean response. So let's say, for example, that we want to focus on the level where someone has a LSS of 5, an IQ of 110, and an EST of, I don't really even remember what these things were, where they were even close to be honest with you. Let's go back and take a look at this. So that would be, let's say that they have an estimated reading level of, who knows, 4. I'll tell you what, let's actually bump up there to a 7. Now, what we can do is we can get a mean response for these values. But gang, what you got to appreciate is if we, for example, brought in 100 kids with an LSS of 7, an IQ of 110, and an estimated reading level of 4, each kid would very likely have a different reading score. So what we're going to do is we need to look at the mean response, and obviously we need to look at the variation. Okay? Now, this gets a little crazy. Nothing actually too awful crazy, but so the first thing we're going to have is we're going to have our okay. All right, guys, let me think about this one for just a second. Lost my train of thought here. All right. So let's take this, which we know is going to be found by taking x times beta. But x in this case is going to be 1, x in 1, x in 2, x in, and let's just call it p minus 1 or k. So for our problem, we're going to have x is going to be equal to 1, 7, 110, and 4. But in this case, our beta matrix is going to be a 1 by 4. Our x matrix is going to be a 1 by 4. So what we're going to have to do is we're going to have to take x transpose, which makes this a 4 by 1, times beta. Yes. All right. So let's get back into R. Equal 4. So we'll call y mean. So the mean response for this is going to be found by okay guys, I'm losing my, so I need to make this let's call it x mean response. Alright guys, I'm drawing a complete and total blank here, what we need to do. It's obvious what we need to do if we've got our regression model, but so if we take x is a 1 by 4, beta is going to be a 4 by 1. All right, let's call this x mean, and let's just let this be 1, 7, 110, and 4. Now what I want here is my x mean vector, and I want this to be matrix x mean in row equals 4, in column equal 1, and by row equal false. So x mean is what we want. So we want, so our y mean predict is going to be the transpose of x mean times our beta. So y mean predicted is going to be 68.3789. Now, this is going to be the same thing if we had done it the other way. And that's just simply put 7, 110, and 4 in our model and come up with the predicted mean. Now, it turns out that the variation for the predicted mean, let me go back and get this. Turns out that I can remember it, for the mean response. Which will be given to us in terms of the variance. It's going to be the mean square error times x transpose h times x transpose x inverse x h. Now remember, this is from before. And of course this is going to be our, I forget, what did we say, 7, 110. And 4. So let's calculate the standard error squared. So now we're going to run into problems multiplying by the mean square error like we did before. So let's just let's just do this. So let's take we called this what, the transpose of x mean, right? Yes. Times now I need to go solve and transpose x. X, and then I need to go times x mean. So then I need to take SESQ. No, it's not going to do this. Let me do the mean square error times SESQ. Oh wow, it actually did. So the standard error here is going to be, the standard error squared is going to be 28.2, or I'm sorry, 28.87. So if I can take the square root of this, 86873, I get 5.371. So guys, finally, we are now set So we're now set to create the 95% confidence interval for the mean response when we predict read from. And LSS equal to 7. IQ equal 110. And EST equal 4. Okay, so let's do this. Now guys, remember, what do we do in a confidence interval? We take our point estimate plus minus our T critical times our standard error. So we've got a point estimate. That's going to be the mean response, which we found to be 68.3789. We've got the standard error, but what we now need to do is we need to now come in and find our T critical. All right, well, that's going to be really easy to do. We can just do this with QT. And QT, we want for a 95% confidence interval, the lower bound is going to have 0.025 area below, and we have degrees of freedom, n minus k minus 1 or n minus p, which is 26. So QT is going to be this. So boys and girls, what we can do is we can take 68.38 minus 2.06 times the standard error, which is 5.37. Then I'm just going to copy and paste this, if it'll let me. And I can just change that to plus, and I get this. Therefore, our 95% confidence interval for the mean response for LSS equals 7, IQ equal 110. So for all those kids out there that has LSS of 7, IQ of 110, estimated reading level of 4, the 95% confidence interval is 57.3 to 79.4. So there's a 0.95 probability this interval contains the mean response for all right. Let me see how I'm working on time here. I think I'm drastically over time. Oh, wow, 139. Yeah, this is a long one. I think I'm going to call it a day. Sorry. Okay. Well, it's either going to be this or divided into two, and I've kind of had a couple of issues that took a little bit of extra time. So gang, this is going to be the end of video 34. And sorry for holding you late.